I think it's time to start. So welcome everybody to the third day of this conference and the day that we're taking some time to think about our friend and colleague Zoe Chatsidakis, who would have been here, and she very sadly she died in January. I don't really want to say anything myself about her. I think some of the speakers today will have some particular words, but I especially wanted to celebrate or to remember her with a party this evening. So I think everybody has signed up and will be coming. So it's at my place between 6:30 and 7 roughly. You'll get there when you get there, of course. So the information is up here. You can find your way with Google Maps. It's a solid 30-minute walk. So if you walk briskly or if you take public transit, that also works. And whatever you do, it always takes about 30 minutes or 40 minutes to get there. So I'll look forward to seeing you all there. There will be some food and drinks, but if people were to bring something else along to drink as well, don't bring more than you can drink yourself. Otherwise, I'll have way too much left over. So please just bring a little bit. And yes, is there anything else I need to say about that? Everybody can find their way. As you come in, there is a concierge, so he probably will just let you in. But if not, then you can give me a call, and I will come down and make sure that you find your way into the building. So after that, I will hand over to Adele, who is introducing the speakers today.
So our first speaker today is Francoise from the University of Mons.
Okay, thank you.
And she will speak about a mouse of correspondence for definable fields and certain fields with a generic derivation.
Okay, thank you. So as Deirdre said, so I was asked by Rahim to speak a little bit about Zoe. So I want first to thank him for giving me this opportunity. And to help myself, I want first to show, I plan to show two pictures. And but before showing them and starting my talk, I just want to begin by saying that I met Zoe a long time ago, while we were both graduate students. So she in Paris, and I was a graduate student in Mons. And we were, I was going to Paris with my supervisor and some other logicians to attend the Paris logic seminars on Mondays. So it's still on Mondays. And there I met Zoe, and she sometimes invited me to sleep over in her apartment near Jussieu. And so how we became acquainted, okay? Okay, so so the first picture. Sorry, okay, I forgot everything. Well, so the first picture I want to show is, I want to show two pictures, and those are pictures that I kept from my own stay in Yale. So I arrived maybe a year later than her. Well, okay, later than her. She was well integrated by then. And this is a picture of her and Peter Papas, who was a boyfriend at the time. And it is during a Yale picnic, some kind of institution. So, so at the beginning of academic year, everybody was gathering, family, professors, students, postdocs, doing this picnic, okay? So I wanted to speak about Yale because I think it was really, so I said, well, sorry, in Paris, she was a student of Gabriel Sabak. And then she made this bold move of deciding to start all over again. So she started over, moved to Yale as a graduate student of Angus MacIntyre. So I think it was a bit courageous of her, because in Yale, she had to take the orals and begin doing everything again. And I think for her, it was not too easy. I mean, of course, it might now that some of us if you get older, it seems a bit ridiculous, but being 2 years older than the others was not, psychologically, was not too easy for her. I mean, so back in Paris, so she first worked on, say, representation theorem, certain structures as rings of continuous functions, and taking specific values on closed sets. So things about Boolean products, so theorems like of Pfefferman-Vogt type things. And from that period, so I think it was published in 79-80, she had a paper called Representation in terms of sheaves of the models of the elementary theory of multiplication of natural numbers. So Scholar arithmetic. But then in Yale, I mean, she started a new project. So a thesis was on model theory of profinite groups. And I think it was taking its root in an article of Charlie McIntyre and Van der Dries on PSE fields and the Galois group and the Topological, looking at the Galois group, the system of finite quotients of these Galois groups. And so, I mean, it was really a big change, but I must say that Yale at that time, so it was this photo was taken during the fall '81. Was really I mean, at least I felt resented it. So I was there because of a travel grant. It was really a friendly, I mean, for me, and I think for her, it was really a friendly place with a really energetic atmosphere. It was a small, I think it's still small, but my department, so everything was more or less in one house, like family house, with a lounge where the graduate students were on the top floor. Angus McIntyre's office was also on this top floor. And I think the nice thing is that everybody was more or less working together. So I think for her, the fact that the graduate courses were not only attended by students, but also by professors or postdocs. And at that time, I mean, I think she learned also a lot of mathematics there. Serge Lang was in Yale, and I stayed in Yale. And I think it was difficult to escape his presence. So, I mean, one thing that he claimed that ignorance for mathematician is no excuse. So you have to learn as much as you can. And I think it just influenced her a lot. And also the friends she made back then just stayed her friends all her life. So the second picture I want to show, it's a party, like today's party. So on the back, you can see, it's not a nice picture, but the picture have, it's Van der Dries, who was been spending the previous year in Yale. He was with Alex Wilkie, and so the previous year there was this course lectures by Jack Titz on Kromos proof on groups of polynomial growths, and later, Van der Dries and Wilkie, we working this proof replace this concept of Hausdorff limits that used by Gromov, and is proved by an ultra-product construction. And it was later known as asymptotic cones. And I mentioned this because Zoe, in a web page, has a lot of notes about also, not all sorts of subjects, but trying to make familiar tools for model theory to other mathematicians. So I think it was a party, so in the house where there were a lot of graduate students, Dave, Laura, Zoe, And I don't know who is this guy. And sorry, well, anyway, and I think it was maybe for, so Lau was leaving, maybe it was a party for Lau. I don't know. And to finish, because I have to give my lecture afterwards. So to finish, I mean, so because of Angus, there were a lot of visitors, and doing this in October of that same year, so Angus was having his birthday, and Carol Wood was inviting everybody to her cabin. So she had a cabin in Cape Cod, and so every logician who were in Liège was invited, and for the weekend in a house. I mean, so and it was really nice. And so to really finish, I mean, so I want to tell one last thing, more in the present. So she was teaching. So Zoe, when got this CNRS position in Paris, and she was teaching a course in the ENS, so École Normale Supérieure. And I must say she loved teaching, and students enjoyed her. I mean, really appreciated her as a teacher. And because she had, it was more or less a little over 2 years ago, she asked me to replace her for her last course because she had to undergo a medical exam that she couldn't move. And so she asked me to replace her for her last lecture. She was teaching a course on minimality. So of course, I said yes, but then I was a bit concerned about what I am going to do. And it was on a result of Zanier, Pila and Zanier. But then I realized that she had prepared everything. So she had filmed herself teaching, giving a lecture by Zoom. So my only role was just to attending with the students the lecture. And in addition to that, she had prepared me to answer the possible questions. So she had given me written notes. I mean, on the theorem she was presenting. Okay, so I think it's just a bit telling of how she was. I mean, okay, so thank you, and I want to go on. Okay, so today I want to describe a joint project with Pantelis and Elliot Kaplan, who started some years ago in Oberwolfach. A small meeting was also attended by Zoe. So it's about definable fields in certain fields endowed with a generic derivation. Oh, okay. So this is rather vague, but I will explain what it means. So the tool we will be using is called the Malsev correspondence between groups and rings, and an analog of pre-group or group chunk constructions, but for fields, or more precisely for division rings. Then, using this construction, we want to apply it to characterize the fields definable in certain generic differential expansion of for certain series of fields where one has characterized the definable fields in them. So trying to relate the definable fields in this. Yes. Oh, sorry, I should do it here. In those theories, to definable fields in the expansion, so adding the derivation. And then the last, I will not talk about the last thing, but just to mention, it's more on the interest of Pantelis, just to mention there are other kind of applications. So it's something he developed for certain O-minimal expansions, assuming that they have open core. So definable sets in the expansion are open definable set in the expansion are already definable in the product. Okay, so I suppose everybody knows small self-correspondence, but I will still recall it. So it's the name showed is due to myself, but I will follow the account of Patrick Simonetta. So what do you do? So you have a group, and you consider the set of inner automorphism of G with a composition. So a conjugation, so it's the set of automorphisms which are just gotten by conjugating G by H. So on this group, you assume that you have an element alpha such that the centralizer of this element is an abelian subgroup. And furthermore, C is normal. So since on C, you have the action of the element of G by conjugation. And the action of G on C is transitive. So given any 2 points, you can map one to the other by this action, conjugation action. Yes? Oh, you mean this?
Yes.
So I am standing in front. Okay, sorry. Which is easy enough. Thank you. Sorry. Yeah, okay, thank you. Okay, so this last line is maybe not so clear, but it plays a role in showing that from this data I will so myself showed how to reconstruct a field. Okay, and this last condition. So okay, I can read it. I mean, just saying that if this happens for an element B of C, for any other element, you have the same kind of equality. Okay, and I will explain how it plays a role, showing that the operation that I'm going to define, you have a high distributivity. Okay, I will explain that. So how you define the ring operation? I suppose you have already guessed. So on C, so C is abelian, so addition will just be defined as group multiplication. Then how do you define product? You just, it's composition of the action by conjugation. So A times B is defined as, so you take, so B is alpha Y. So remember, the action is transitive. So any element of C alpha has this form. The centralizer of alpha is this form. So you take B and then you conjugate it by X. So where X is is how you get from alpha to A. Okay. So well, you can say, well, it's not well defined, but because of course you can have several X. Alpha can be expressed as A, can be expressed as alpha X prime, but because C is abelian, it doesn't matter. Okay. So to explain to you, so when you show that addition and multiplication defined in this way, it's a division ring. Okay, so we don't assume that multiplication is commutative necessarily. And so how to show, for instance, so left distributivity is immediate, but high distributivity, so you have to show this. So you take X, Z, X, Y in G, such that D is alpha Z, B alpha X, and B prime alpha Y. Then remember, you define multiplication taking D and conjugating by X when X is related to, is how you get from alpha to B, conjugating by X. Then the other product is defined in this way. And now you have two cases. So in the first case, you use this third property. So since the action is transitive, I mean, this product stays in C, so you have some W such that this equality holds. And so by free, this holds for any other elements. So the other element will be alpha Z, okay? So what is this? So this is just B plus B prime times D, and this is B times D plus B prime times B prime times D, okay? And in the other case, I just the fact that minus just go across. Yes. Sorry. Oh, sorry. Multiplication is sorry. Sorry. Okay. Multiplication is defined like this. So you take B. Sorry. Alpha is some element. Yeah. Well, okay. I didn't say that it was a proper subgroup. Yeah, you're right. It is okay. I can write it on the board. I mean. Okay. Okay. And so in the other, so I showed you for certain groups, for certain soluble groups, we can reconstruct a field. And those groups are in fact, and now I mean from a division ring out, what is the associated group? So you just take the 2x2 matrices with coefficient in K. Also, it's like also you can view this as linear maps AX plus BY. Oh, sorry, AX, yes, plus BY. And so you can check that this group of matrices satisfies all the properties. And you can also view this group as the semi-direct product of the additive group of K, which is these matrices by the multiplicative group. Okay. And for alpha, you can just choose any matrix of a form 1V, for instance. With, I suppose I should have said V, not 0. Okay, and what you show, so here there's some calculation that I'm going to pass. Well, you can check 3, this third property. So one can easily see that you have this isomorphism between of the two operations. I mean, you can recover multiplication of K by this funny way of defining multiplication. And here you can see what happens if you conjugate this matrix by that one. You have a product appearing in the second term. Okay. And then you show that doing the previous construction, the division ring that I started with is isomorphic to this subgroup endowed with these two previously defined operations. Okay. Okay, so now, I mean, how are we going to use this? So what are the 10 series of fields we are going to consider? So we work, let me just skip this. So we work with in a saturated model, so universal domains, and we assume that the algebraic closure, so I said the model theoretic algebraic closure, but if my language was just the language of ring, it would just be the usual algebraic closure, satisfies the exchange property. And why we do this is because then you can define a notion of dimension on the tuples, just saying that you take, given a tuple of elements of your field K, you say a certain dimension is the length of the longest subtuple, which is algebraically independent. And then you define dimension of subsets as the supremum of the dimension of its elements. And I'm telling you this because then you have naturally a notion of large subsets. Just so X is large in Y if it is of the same dimension, and also its complement is small. Okay, so if you have two intervals, one of them is not large in the union, for instance. Oh yes, and the notion of generic elements are just the element of maximal dimension in the set X. So in the talk of Omar yesterday, we heard a little bit about this. So what is this pre-division ring construction? So I suppose I want to go to the next slides first. With this notion of pre-group construction due to veil. So the idea is just you don't have a group, but you have almost a group, and almost means that on the generic elements of your set. So you have a set, which is definable. You have two operations, two maps, F from X times X to X, and F minus 1 from X to X, which satisfies these properties. And it just means that on generic elements, these two maps act as, for F, the multiplication, and for F minus 1, the inverse. Okay, so it's what I try to express here. So, every generic element is in the domain in the inverse. The inverse, if A is generic, the inverse is generic, and it's an idempotent map. Multiplication is defined on generic elements. You have generically associativity, and you have this kind of cancellation property, which means that if you first multiply B by A and then we multiply by A minus 1, you get the identity. And this is from the right and the left. I mean, this is not the most economical way to present things, but I think, well, for me, it's the easiest. And so now, I mean, that we know that what a pre-group is, what is a pre-division ring. So as you might expect, now you have two operations. So multiplication denoted by F and addition denoted by A. Yes? Oh, yeah, sorry. Sorry, I should have changed. Yeah, yeah, sorry. I didn't change it. I noticed that I used A for the parameter set, and it's really a bad idea because A denotes the addition, okay? So on the next slide, the previous slide, I changed A with C, and I forgot to change it here. Or just some parameters, it doesn't matter. Oh yes, and of course, and thank you for pointing this out. C has nothing to do with this subgroup I was talking about. So I make things complicated, and so thank you, sorry. Yeah, no, C is just, sorry, A, okay, so forget about, so assume that LA is just L, okay, sorry, just certain parameters. So you have two operations, F, multiplication. No. Oh yes, sorry. Multiplication and addition. So you ask that you have two pre-groups on X, and you ask what else do you have to ask? Some compatibility condition between the two operations. So the compatibility conditions are the following ones. So you ask that the minus gets across, okay, so which is with two conditions. You still want that one of the operation is commutative, so this is expressed here. And then you want, as you might expect, generate distributivity from the left and the right, okay? And under those conditions, which are expressed in terms of generic elements, you say that if you set X is endowed with two operations satisfying these conditions, or the natural conditions, you have a pre-diffusion ring. Okay, so now the game is to reconstruct a division ring from this data. So you follow Merz construction. So you consider 2x2 matrices with elements in X. Of course, I mean, so I define everything in terms of generic elements. So you don't have a 1 or a 0, okay? So you just define those elements by the way they are acting. So you had two elements, I mean, the way they are acting on your set X, okay? And so you denote the set of matrices by T to X, okay? And the first thing you show is that the condition you put are enough to show that this set of so x times x with, so then this denotes matrix multiplication and the inverse operation for matrices defined using these maps A and F that I had before, okay? And as before, you have this matrices of a form 1B and the diagonal matrices 0A, okay? That will correspond respectively to the additive subgroup and multiplicative subgroup. And so now I mean, I define everything in terms of generic elements, and I want to translate this as by the fact that these elements act in an expected way on large subsets of X. So first on X squared or possibly on X, okay? And so we call that the operation were not defined everywhere, but for generic elements, so translated on large subsets. And so you act, this pair of elements of X, so, or this AB in X squared, acts on X squared in the following way using these operations A and F, okay? And of course, I mean, this is not defined everywhere, so it's why, I mean, we don't have really a map, but a germ, okay? But you can compose this germ and you have the group of all permutations, so germ-like permutation on X times X. And then you show that even for, I mean, these maps are defined on large subsets, that really you have the map sending, you can define a large subset of X, so this is V3, sending A to this matrices, diagonal matrices A0, and B, this map B sending, and the map sending B, sorry, to this upper triangular matrix 1B. Those two maps are well defined, okay? So you can define a large subset on your set X so that this holds. Then on these large subsets, you have a well-defined map sending AB to this 2x2 matrix. And from now on, we will allow ourselves to identify these elements by its image. So its image is a germ acting on X and X. And so previous result which appears in a paper by Kobe Petersil, Anand, Pillay, and myself. We showed that if you have from a pre-division ring, we went to a pre-group. So we can use result on pre-groups. So we showed that from this data, pre-group data, we get a definable group. And you might, I mean, in principle, the group of permutation, you need any number of elements of permutation. But we showed that we can just restrict, we want to get a definable object. So we show that we can restrict to the product of two elements. And so X, so I told you that X was endowed with a dimension function. So we show that in fact, this group G, well, we have to show that you have definable operations using this previously defined F and A. And you show that G can be, in fact, covered by a finitely many translates of this kind of elements. So now the game or the job is to show that this group is the right one. And because of this Maltsev correspondence, that I explained before. I mean, this result is not too surprising. So, so you take alpha, an element of a form 1 corresponding to a matrix upper to a triangular matrix 1U, when U is a generic element of X. You consider the centralizers of this element in G. So this you have to show that the centralizers is really what you expect. So this upper triangular matrices. That it is a normal subgroup. So G acts upon it by conjugation. The action is transitive. And then you have this third property, which is used to show distributivity. So from this data, as I showed you, one can define two operations on these centralizers, on this centralizer, and the two operations are division rings operations. Okay, but maybe I don't know. It's not too easy to show. It took us a while to show these properties. I don't know. Well, anyway. Okay, so from that, so let me recap. So you start with a pre-division ring. You construct this pre-group of 2 by 2 matrices, upper triangular matrices, and then you show that on the subgroup you get field operations, except that multiplication is not necessarily commutative. Okay. And then the operation you define coincide with the original operations. So then, I mean, okay, we did that. So to which theories are we going to apply it? So here I put some results where indeed one knew what were identified for definable fields in these theories. So first case is all minimal theories, like theories of real numbers or expansion of real numbers by restricted analytic functions. Margarita Otero, Kobe Petersil, and Anand Pillay showed that, well, it's a string, a long string of results, but the final one that I'm using here is the following. So if you have so it's a little more general than the situation I will be working with. So if you have a definable ring without zero divisors in a non-minimal expansion of a real closed field, then this ring is a division ring. So you show this using DCC in this theory. which is either K or an algebraically, so K is real close, an algebraically closed field, or the division ring of quaternions over K. So nothing new in some sense. So then the second result I want to mention, which was much later. So if you have a real close valued field, so you have a real close field, and you add a valuation or a predicate for a valuation subring. And if you have a definable field, it's also, so now I'm assuming commutativity is either K or the algebraic closure of K. So a much earlier result of Anand, which was following what he did for real closed fields. So if you have a definable fields in a periodically closed field, so say QP, then again is isomorphic to a finite extension of K. And more recently, so it's just a special case of the result because they are not only considering, so this is in some sense the easy case in what they are doing. So it's a result by Yatira Levy, Asaf Hassan, and Toby Petersil. So I suppose I don't want to define what is a DP minimal thing, but so if you take a valued field which has some undot, well, so let me say it without explaining it. So a DP minimal expansion of non-trivially valued field of characteristic 0, and you consider infinite definable subfield, infinite definable field in some powers of K, then it's also definably isomorphic to a finite extension of K in, so if we're adding condition on this adding condition, so V, I will not say again V minimal, but it will come back. I will come back to it later. So it's, for instance, it's algebraic closed valued fields. It's an example. Or power bounded T convex valued fields. So it's an easy case of this is RCVF, real closed valued fields. It's more general. So as I said, it's it's an easy case of what they're doing. They're really looking at interpretable fields, okay, not just definable ones. So now, so I was telling like a sample of result that people got in TIM series of fields. So now how are we going to apply it to characterize fields in the differential expansions? So by now, I suppose you're familiar with these notations. So CK will denote, as in Christine's talk, will denote the subfield of constants. So possibly we apply the derivation a number of times. Nabla M of A is just a finite sequence of, so the prolongation of A by taking the successive derivations of A. And you have this for an element and this for a subset. Okay. So now, what do you do? So you consider, so Fion says a real closed field, and you add to it a derivation, and you denote the expansion of your structure by M delta and M partial. And you consider the theory just consisting of a theory T plus the fact, plus the V information that partial is a derivation. But I didn't really spend time on it, but possibly you have other functions than the field functions, the ring one, say. So you have also to tell how the derivation behave with respect to the definable functions that you can have in your language. Okay. It's allow you. It's a more or less. I don't know. It's making your life easy. So the notion of a compatible derivation, which has been recently used by Francoise and Kaplan, tells you this. So if you take f, so f now is a definable function defined on an open set. Well, assume that I am in a, well, I suppose I didn't say it. So let me work now in a field when you have some kind of topology, okay? And what I suppose I didn't really say it, but so the notion of partial derivatives makes sense. So you're assuming that the partial derivatives exist and are continuous. And so what you ask about the compatibility condition on your derivation and the functions of your language are the following. So you say that to calculate the derivation of the image of u by f, you have to calculate the partial derivatives with respect. So f was from u1 applied to n tuple times your derivative applied to the elements. So it will enable you to show that if you have a term in this expansion by the derivation, this term can be really expressed as another term in the reduct, so in the language without the derivation, but on u with variables u and delta of u, or partial u. Yes?
Is it the case, maybe you said this, but A here is a constant parameter?
No. Yeah, and so thank you. So A is, so in this line, A is empty set. And when there is a twisting, it's exactly on the next slide, okay? And this twisting. So this trick is, for this extra term, you just think about when f is a polynomial, when you take the derivative of this guy, you have also to take the derivative on the coefficients of your polynomial. Okay, and I mean, so the theory you will be looking at, if you have extra function besides the ring language, you ask that the derivation is compatible with functions defined on the empty sets with no parameters. And life is not too difficult. I mean, you say, well, then I have a long list of axioms, but as shown by Francoise and Kaplan, this property is closed under composition and the implicit functions here. So the assumption on this differential expansion I'm going to make is the following. So, so this one has been explained by Omar yesterday. It's just maybe it's a way to express that on algebraically independent element, you can define the derivation as you like. But when you have an element in the algebraic closure, the derivation is given. We have no choice. So this last condition was what you explained yesterday. And that one is just the usual property, the usual field property. But here, I mean, we are working in possibly expansion by other functions than field functions. That's why it's more complicated. So now you assume, so here, I mean, yesterday, so Omar was explaining to us how to get existence of a model companion, or what are the question he asked yesterday is what are how can you describe the existentially closed models? So here I'm just going in the opposite direction. I suppose I do have a nice theory, so the expansion by this derivation as a model companion. So the class of existentially closed models is it's elementary, so it's closed under a product at images. And this was, for this kind of series with just one derivation, and one derivation is not essential. It's been done in a number of cases. For instance, you have R with real numbers with restricted analytic functions. You can also consider add the exponential functions. You have a theory of QP and Simeon fields of characteristic 0, algebraically closed valued fields, so fields of this form, real closed valued fields, so ordered fields of this kind. And another example which doesn't quite fit, which was recently studied by Nigel Pincoats and Elliot Kaplan. So in those previous examples, the derivation was generic. Even for, all these examples, I think I forgot to say, was just in the context of topological fields with no a priori assumption on how the derivation behaves with respect to the topology. So here, so it's a field so it's an ordered field with prescribed with a fixed valuation ring. One assumes that the derivation is continuous, which means that it sends the maximal ideal of the valuation ring to the maximal ideal. So it will imply that on the residual field of this field, it will be endowed with the derivation. So this situation is unlike the previous ones, but since this case, they have similar results that the one that is right, I just wanted to mention this. And for this series, you also know the definable subfields. What are the definable subfields? Okay. And still the two other conditions between the natural ones is that a manifestation of what I have been telling you for terms, but just now for any formula, is that you can rewrite any L formula in terms, and so any L delta formula phi in terms of an L formula, but not with x as a variable, but with this prolongation x, partial of x, partial m of x. And the last condition, which is in some sense a real condition, is well, it's not always satisfied conditions. So it's asking that if you have an element in the definable closure, so of your set X in this expansion, is it in fact in the definable closure, in the reduct, in the language without the derivation, in the prolongation of X? So under all these conditions, you can get this result. So you have a del delta definable division ring in this expansion, assuming that this theory T partial satisfies all the is nice. So this, furthermore, this definable set is finite dimensional in the sense that there is some m such that when you look at its prolongation, it is ending up in the algebraic closure of the first m prolongation. So under this condition, you can find, so this theorem, this kind of result have some extensions. You don't necessarily need to assume this, but at least as far as I know, to get a definable objects, I think it's only known under this kind of conditions. So you get now a definable division ring, which is close to what the one you started with, in the sense that gamma densely embeds in this L-definable ring. So what does mean densely embeds? So in the context I've been describing, you start with topological fields. So it's dense in the topological sense, and it's also dense in, you can also define dense in terms of generic elements. Okay. So it has an abstract definition. And so the method of the proof is that, so you assess, so given all the conditions, all the relationships that I described between the expansion of a language and the language you started with, okay, so you first associate with this L partial definable object a definable pre-division ring. Then you apply this construction, going from a pre-division ring to a definable object. So you get this, remember, you get this 2x2 matrices. So you get a pre-group and then a definable group living in this, in X times X. Then we're using this Mal'Sef correspondence, getting a division ring living in these centralizers of these 2x2 matrices. So the upper diagonal matrices. And finally, I mean, we show that, which I didn't quite explain why, how, I mean, one can so you get this division ring is in this subgroup. Then with this division ring, you can associate this group of matrices, this prolongation, and you show that it densely embed in this L-definable group. Okay, and this since everything is more or less canonical, you have a group that embeds, but also from the group we construct a division ring, and this goes down to the fact that the prolongation densely embeds as a division ring in this subgroup. Okay. Okay, thank you.